Good evening, and welcome to this broadcast of the Phillies Emergency Teaching Network. What you are about to hear is the lecture that I would have given today on springs. What you are going to see is my handout on springs, and I am going to go over it one piece at a time, explaining in at least modest detail what is going on. Hopefully you'll get something out of this, and we will not fall any further behind in the course due to our wonderful winter weather. Nonetheless, this is the Phillies Emergency Teaching Network, and tonight's broadcast is on springs. We are now going over my handout on springs. All of you should have been able to download the handout from my web pages at wpi.edu/Phillies. If you haven't, you should consider doing so. Springs, I confess, are not a topic I am fond of talking about because it is very hard to talk about it clearly and precisely. It is much easier to give you an incorrect impression of how springs work, an impression which I can hide in terms of hiding the errors by cooking the homework problems so that you'll get the right answer even if you don't know what you're doing. That's sort of clever, but it's not good physics. So let us start at the beginning, and at the beginning we have to introduce the notion of masslessness. Now, one could propose that there are things that really do not have any mass. Photons don't have a mass, they have a mass of zero. They create a gravitational field and they interact with massive objects, but they have a rest mass of zero. It was for a very long time believed that neutrinos have a mass of zero. However, current modern studies, the resolution to the so-called solar neutrino problem or scandal, have shown that it appears that neutrinos actually do have a very teeny tiny rest mass and therefore move only approximately exactly, but not quite, at the speed of light. We're going to, however, talk about masslessness in a sense that Isaac Newton would have understood. By masslessness, we mean that the mass of some object is sufficiently small relative to everything else that's going on in the problem that we can ignore its mass. So if we have two cars and we've hooked it together with a tiny piece of Kevlar rope, and the two cars weigh several tons each, and the Kevlar weighs some modest fraction of a pound, the total weight of the system is very nearly the weight of the two cars. That's masslessness. A mass is massless. We have a masslessness condition if the mass of some object really has more or less no effect in the outcome of the calculation. So you change the masslessness mass a bit, and you discover the calculation doesn't change very much. Now, negligible sounds very simple, but it's decidedly not trivial. Our understanding of what not trivial means has actually changed quite substantially since I was an undergraduate. The core issue is that in the sort of mechanics problems you've done, like the falling object, the outcome of a calculation depends on the input mass, the input numbers, as some polynomial in the masses. So if you change the masses by, say, 10%, the calculated answer will also change by some number like 10%. Maybe not exactly 10%, but something like that. However, there are other mechanics problems that are exponentially sensitive to input parameters and that have answers that diverge exponentially quickly from each other as input parameters are also changed. In these problems, a 10% change in mass does something huge. In this course, we mostly stay away from these other problems. Billiards is a good example of a case in which input parameters can be very sensitive. If I fire one billiard ball at another, and I don't hit the ball straight on, center to center, if I hit slightly to the left or slightly to the right, the outcome in terms of where the next billiard ball goes can be rather dramatic after not very long, because the ball heads off to one side or the other. It turns out that planetary astronomy gives us good examples of problems that aren't stable the way you would think from our simple falling body problems. For example, there are reasonably good calculations showing that the orbits of Mars and Venus wander in and out by tens of millions of miles from where we now see them. It might be the case, I'm not sure where the settlement of this calculation finally was, that if you wait long enough, you will be able to see the planet Venus with the naked eye as a very clear disk, just as you currently see the moon as a disk. However, you might have to wait a while to do that. Okay, so let us consider what masslessness means in practice. Suppose we apply a set of forces to an object whose mass becomes really tiny. Newton's law of motion tells us that G, force equals mass times acceleration, doesn't it? And therefore, if we apply several forces, because the force in Newton's second law is the total force, if we apply several forces, the total force is still mass times acceleration. Of course, this is the grown-up course, so we are using the grown-up symbol for acceleration, not the little kitty symbol for acceleration. Now, what happens if m becomes negligible? In that case, Newton's second law has a unique solution, namely if we have two forces applied to a basically massless object, the two forces must be equal in magnitude and opposite in sign, because they have to sum to, for all practical purposes, 0. Some of you will be looking at that and thinking, gee, that equation looks just like the forces in an action-reaction pair, doesn't it? Yes, it does look like the same equation. However, F1 and F2 applied to the same massless object cannot possibly be an action-reaction pair. They cannot be an action-reaction pair because the forces in an action-reaction pair always act on two different objects. These forces act on the same object, so they cannot possibly be the forces of an action-reaction pair. And now we are going to discuss massless springs. So there you see a massless spring with two forces, F1 and F2, being applied to it. The forces are being applied because someone is hanging on to it and pulling on both ends. F1 and F2 are the forces on the spring due to the two hands. This figure illustrates several points that sometimes get lost. First of all springs have two ends. The length of a spring is determined as the difference in the location of the two ends. So if you say a spring has a length x, you can't at the same time, without being very careful or going wildly off the rails, say that the location of the end of the spring is x, because you have to say something about where the other end of the spring is. The other issue here, as I've pointed out, is that a spring applies the same force on both ends. So suppose we took a big spring and attached it to the ceiling and hung a weight from it and poked the weight so it would bob up and down. It's not a pendulum, but it is something that oscillates up and down, up and down. You want to remember when you did this that whatever the force being applied to the weight is, the same weight is force is being applied at the other end of the spring to the ceiling. Now, if you've carefully drilled a hole in the ceiling through the concrete flooring, run a bolt all the way through, and have a capture plate on the far side, you may annoy people because you drilled the hole, but it's secure. On the other hand, if your idea of attaching the spring to the ceiling was a teeny tiny little screw that you put into the acoustic tile, you may discover that when the force is applied to the acoustic tile, what happens is that the far end of the spring pulls out of the ceiling. Yes, springs have two ends, and this matters. Okay, so there are two forces here. Each force must have a reaction force. What are the two reaction forces? Well, the original forces, what were the original forces? The original forces were being applied on the spring by the two hands. The spring is massless, so the two forces happen to be equal. But since the original forces are applied on the spring by the two hands, the reaction forces are necessarily applied by the spring on the two hands. And here are the two reaction forces. And you notice the two reaction forces are applied on the hands and are the same as the original forces, except, of course, the signs have flipped. In this figure, I don't show the spring, so you can see the forces on the hands. But you should realize that there is indeed a spring, invisible spring, supplying those two forces. Okay, how big are those forces? Well, that answer was actually supplied by Hooke. Hooke was a contemporary of Newton. Hooke was asked to solve the question of how comets move, and proposed that comets move in ellipses, and sort of proposed that the motion was due to gravity, and rumors of this got back to Newton. Newton had solved the problem a long time previously. He looked at things and realized he had to rush his book into press or he would lose priority. To put it mildly, Newton was sensitive about priority claims. Indeed, some people suggest he wasn't quite normally mentally balanced when this sort of topic arose. Newton was also sensitive about all sorts of other things, but that doesn't matter here. Nonetheless, Hooke did explain springs, and Hooke's law springs have the interesting feature that they are, well, first of all, they're quite ideal. A Hooke's law spring can be stretched or compressed. You stretch it, you compress it, it delivers a force in accord with Hooke's law exactly. Real springs are not very linear. However, finding the solution to Newton's laws of motion using linear springs is already quite challenging enough that we have our own course on it. It does other things too. Physics 4, oscillations and waves. But let's stay with an ideal Hooke's law spring. It has two parameters. It has a spring constant K, and it has an equilibrium length L0. The equilibrium length is the unloaded length. If there are no forces on the spring has some length. Now, let's suppose we just have a spring that's attached at one end. In that case, the other end isn't attached to anything, and there can be no force on the other end. However, the forces on the two ends of a spring are equal in magnitude and opposite in direction, so a spring that is only attached to things at one end can have no force applied to either end. Okay, so we have a Hooke's law spring. And here is a picture of a Hooke's law spring. It's right in the middle. The force generated by the spring is a restoring force which attempts to move the two attachment points until they are separated by the unloaded distance. If you stretch a spring, it pulls in towards the middle. If you compress a spring, the spring pushes objects back. The magnitude of the force generated by a spring is K L minus L0. This force generates a force of this magnitude at each end of the spring. So if we have a spring of equilibrium unloaded length L0 and attach it at each end to masses M1 and M2, you notice I have stretched the spring. The forces on M1 and M2 in magnitude are both K times the change in the length of the spring. But you'd better look at that carefully because you notice that, yes, M2, the force is minus K, L minus L0. On M1, the force is plus K, L minus L0. And, of course, the forces are vectors. There's an I hat in there. Where did the sign come from? How do I decide whether to stick in a plus or a minus? And the answer is we have one of these problems in which you have to actually look at the quantities, ask what happens when the quantities are all, say, positive, and then put in the sign by hand. Well, you've done this before. Suppose you have a mass on a ramp. There is a force of gravity whose magnitude will, in the units and we've usually used, be mg sine theta, pulling the mass down the ramp. Is the force going to be plus mg sine theta or minus mg sine theta? Well, it depends. Which way did you put the axis along the ramp? Uphill or downhill? It matters. In this case, you have two masses and a coordinate, and you actually have to ask yourself which way the force is going to point and choose the sign correctly. I am now going to detour. There is a standard error. We detect the standard error by giving large numbers of freshmen. Actually, this would apply much more to 1110 than 1111 students. Fairly simple questions, and we discover they occasionally come up with odd ideas. One of the odd ideas is as follows. The force generated by a spring is, it says so right here, K L minus L0. Somehow people get the idea that force is divided between the two ends of the spring, so you pick up a factor of a half because the force has been divided. No, that's not what happens. The K L minus L0 is the force determined, generated by each end of the spring. Of course, that's the magnitude. The two forces point in opposite directions, but the force is K times the change in the length of the spring, not K over 2 times the length of the spring. Another standard error, which I've sort of discussed once, is to forget that when you have a spring, it generates a force at both ends. So if I am holding a spring, and I move my right hand to the right, I've made the spring longer. And therefore, there's a force due to the spring pulling my right hand back to the left. However, when I stretch the spring, I now have a force on my left hand, too. It's a force of exactly the opposite magnitude, exactly the same magnitude, but it points in the opposite direction, because both ends of the spring are being pulled into the center. When you are setting up problems, you want to be sure that when you have inserted your spring forces, they pull to two masses attached to the two ends together, or push them apart. If the two masses were parallel to each other when you stretch the spring, the two masses would have forces on them in the same direction. They'd take off faster and faster off into the distance. NASA will be delighted to buy one of these from you if you can build them reproducibly. After all, reactionless space drives only work in Star Trek, and they'd love to copy Star Trek. Okay. I have been discussing springs that lie along the x-axis. In general, a spring lies in some arbitrary direction in three-dimensional space, and you have to break the spring forces into x, y, and z components. I'm going to be honest. This is one step too far for this course, so I'm almost always going to dodge that and say the spring lies along a coordinate axis. It's already enough to get down what happens next without putting in some spatial geometry, which really doesn't add anything much to the physics. Okay. Suppose you want to specify how long the spring is in terms of coordinates. Well, the two masses 1 and 2 have locations x1 and x2. That's not new. And therefore, the length of the spring would appear to be x2 minus x1. But we have to be a little bit careful here because the length of the spring is a positive number. That's how length is defined. x2 minus x1, well, it depends which mass is on the left, which mass is on the right. x2 minus x1, if you're not careful, could be positive or negative. And therefore, when you write the length of the spring, you may want to write it as x2 minus x1. You may want to write it as x1 minus x2, but you'd better think a bit about what you're doing so you have the force, the length of the spring right. And here we have an example. There is a spring with x1 and x2, and I've put x2 and x1 in a natural order, so if you say the length of the spring is x2 minus x1, the length is a positive number and everything works. What if you get it backwards? What if you say that the length of that spring is x1 minus x2? Well, if you calculate x1 minus x2 minus L0, x1 minus x2 is a negative number. If you subtract L0 from it, it's an even more negative number. And now you have the interesting feature that if the two masses are separated by L0, the force doesn't go to zero. You actually have to get this right by thinking about what you're doing. Ditto, if you are putting the signs in front of K, you'd better get the forces pointing the right ways. It's like the ramp problem. You actually have to think a bit about what you're doing. Bunches of you learned in high school and were brainwashed into force equals minus Kx. Well, it depends. Which way is x? Which end of the spring are you looking at? The force is minus K, change in length of the spring at one end, and plus K, length of the spring at the other end. Now we come to an amusing and subtle but very important mistake. Suppose you had the bright idea, this is a perfectly reasonable idea, and it involves some very delicate physics which we haven't stretched much. Suppose you said the coordinate of the first mass was x1, and then you said that x2 was the coordinate of the second mass using the first mass as the origin. Gee, now x2 minus L0 is going to be the change in the length of the spring, isn't it? Well, there's a little difficulty. M1 is not nailed to the center of the universe. It's free to accelerate. As a result, the coordinate system you're looking at here is not an inertial coordinate system. It is not a coordinate system in which the origin does not accelerate. Because it is a non-inertial coordinate system, well, you can write the force due to the spring this way, but you've got a little problem, and the little problem you have is that Newton's second law of motion is not valid in these coordinates, and therefore you can draw this picture, but if you try to solve for the motion of the masses, it won't work. Well, it won't work unless you understand how to insert some fictitious forces, which we are not going to talk about in this course. So don't do this. Be sure your coordinate origins are nailed to the ground where they belong. Okay. Now we come to the last issue, which is also one that I'm not quite fond of. Here we have a mass hanging from the ceiling. And I am not going to do all the math in fine detail because it's just tedious, but I'm going to point out what is going on. So here is the spring, and the spring has an unstretched length. And we now attach the mass to it and let the mass sag and come to rest. When it comes to rest, the mass has displaced a certain amount from where it started. It's displaced from its unstretched length. The spring is stretched and it's applying a force K delta Z upwards. And that force K delta Z upwards, you've got to decide how to do the signs depending on which way delta Z points, cancels the force of gravity. And therefore, if the spring is just hanging there, there's a force K delta Z up, a force mg down, and the sum is a 0. That's good so far. Now we come to the hard part. Suppose we then say we are going to displace the mass from its equilibrium position, where the two forces were adding to zero. In that case, there is an additional spring force due to the motion of the mass relative to its resting point, and that additional displacement of the spring gives us an additional force K delta Z. If I write the force diagram for the mass, well, we start at the unstretched length, we sag down to the equilibrium length, the spring is giving an upwards force, gravity is giving a downwards force, those two are adding to zero, and the only net force I have left is the K delta Z, the movement of the mass from its equilibrium position. Not its unstretched location, its equilibrium location. And therefore, we can draw the force diagram like this. There are two hidden forces in the force diagram. One of them is the force of gravity. The other is the displacement of the spring down to the so-called equilibrium length. Getting all those signs and details right is something that I will do if I teach Physics 4 again. And until then, all you have to be aware of is that you want to think carefully about what you are calling the origin. So that is my lecture on